at the gate station, we'll have a connection to Williams, and Intermountain Gas will take over custody of the gas. We will regulate and odorize it. And typically those gates feed our high pressure laterals, which are in red. High pressure, again, just so we're talking the lingo, that's operates over 60 pounds. And then off those high pressure laterals from the gates, we can directly serve large volume industrial customers, or, they'll go to our regulator stations, and our regulator stations will cut down the pressure, typically down to distribution pressure. And then kind of the piping in blue is our distribution system. That's typically where we serve our residential, our commercial, and we also can have some large volumes off of distribution systems. So the 60-pound systems, and typically downstream of a regulator, to get the gas down the system, you'll usually have larger size trunk lines out of the regulator station. Could be 6-inch or 8-inch or 4-inch. And then as you go down the system, that'll reduce down to maybe 2-inch, in the neighborhood or the subdivision, That kind of sets us up. And then all of this, our whole system, we model basically in synergy. So synergy allows us to model for growth and identify our deficits, make sure our system's performing, reliable and in the manner, in good operating condition. And we use Synergy Gas to do that. Synergy Gas is distributed by DNV, and then our models incorporate all of our customer loads and all of our existing pipe and system configurations. And really, it's basically a hydraulic modeling software that allows you to predict flows and pressures on the system during that peak weather event. We also call this a design day. So your coldest weather event, that cold morning, is when our systems typically peak. For Intermountain Gas, our models are updated every 3 years and then maintained between rebuilds. And then I'll just give an example. So this is kind of Synergy Gas. So this is actually a screenshot of our GIS data. You can see here, distribution pipe is blue, and then steel pipe is green. And then you can see little regulators. The little red circles with numbers are regulator stations. So that, if you follow those regulator stations, that's kind of the high pressure lines. So you can kind of see how our system flows and feeds the distribution. So all of our systems are unique in their customer served and their pipeline characteristics. And we basically take all this GIS data and then turn it into Synergy. So this is Synergy. It looks really similar to GIS, and you can see the regulator stations are the little triangles. And then this is blown up a little bit than that last image, but you can see the gates are the circles. So you can kind of see we got a high pressure lateral that runs, southeast, over on the left side. And then some distribution pressure you can see in the middle.
Excuse me, Kathleen, we have a question from Rick.
Hi, Kathleen. I have just a couple questions. You referenced you have a compressor station. Could you explain what that is for?
Oh, sure. I'm going to get into compressors, but yeah, compressors will boost pressure on a lateral. So we have one currently and one in construction and then one proposed, but our current compressor station is on the Sun Valley lateral. It's just north of Shoshan.
Okay.
So compressors will boost pressure. So if a long lateral, so that lateral is, gosh, I think it's over 70 miles long, but we have the Sun Valley lateral runs from Twin Falls all the way up to Ketchum. So on those large laterals, compressors, instead of running another pipeline, you can use a compressor to boost the pressure. So maybe if your end of line pressure isn't high enough, you put a compressor that would compress the gas and boost the pressure.
Thank you. One other question with respect to your modeling software, what level of granularity does it provide? Do you see individual residents in your design?
Yeah, I'm going to cover that. We don't do, so the models are big and they take a lot to run. So we don't include the service lines, but we have our customer management module actually takes the service lines and applies those loads to the pipe. So it's kind of a way to make the models run efficiently and not have too much data or crash, but you still get the loads spatially applied.
Okay, thank you. I'll let you move forward with your presentation. Thank you.
No, we're gonna go through, we're gonna keep hitting synergy a little bit, so I think, yeah. Feel free to ask more if you got them. And like I said, so our synergy, we have a massive building process, because these synergy models are so important. Like I mentioned, we rebuild them every 3 years and then we got to maintain them. So if we call them CLSs, but if any large volumes customers come on, we want to make sure all that's accounted for and up to date all the time. So our engineers, that's part of their regular responsibilities. And then when our models are rebuilt, we export out the current GIS data to build the spatial models. And then we also export out 5 years of our CC and B billing data to CMM, which is the customer management module. And that creates that updated demands file that I just discussed that basically loads the pipes. So they'll take all the service points, all the meter points, put them into the pipe. And then once we get that build completed, we will validate and calibrate each model to a recent low pressure event using all the data we have. And we have ERX data, pressure charts, SCADA data, Metrotech data, and our large volume usage data. So we want to make sure our models are dialed in and kind of performing correctly. And then once we get that process, and typically for model building, a best practice is to be within 10% of actual data. So that's the metric we aim for. And then once we have that calibrated model, we then ramp it up to a design day, because it's very rare that in the last 3 years we would hit a peak design day and have that data. It'd be great if we did, but typically we're not hitting design days, which is good. So then we build those design day models up, and we're based. And I have another slide to talk about this some more, but we get the design day, or I guess our coldest weather event predicted for the areas from regulatory. It's based on historical trending, and then we use that to kind of ramp the model up to that event. And our IGC models were rebuilt in the fall of 2021, so getting close to due for a rebuild. And then I just got a couple slides just to show a little more. This is some of the data gathering. So this is just a screenshot from CC and B, which is our customer billing data. So this is someone's bill, or kind of our database on billing. So we work with our programmers. So we ask for a data request and send this in to Synergy, and then they build our that demands file in CMM. But it's just an example. Take that 5 years of data, and this is just another example of some of the data gathering. So when we calibrate, we use all of our existing data, but this is a screenshot of our SCADA view. So for all of our large volume customers, we know we have historical and real-time data on their flows and their pressures. We have gate flows. We have various pressure charts in the system that are there just to help us dial in these models and have a really good understanding of our systems. So it's just a screenshot from some SCADA data that's available. And then this is kind of where we're going, but I'll expand a little more, because this one can be a little tricky. I think I've used this term a couple times, but I want to go over what a heating degree day is. So right here's the equation. Every day has a heating degree day. Our systems we build to the peak heating degree day. So you can see in this table, these are our peak heating degree days that our models are designed for. You can see we operate through a diverse range of, we got mountains and desert. You can see, Ketchum's up in the mountains, up on, up where everyone skis. So it's pretty cold. -17 is what it's designed for. And then you can also see it gets pretty cold in Idaho Falls, whereas Napa, not as cold. So this is the historical weather we're given that we ramp the models up to. And when you take your heating degree day, it's always based on 65. and this is industry standard, but 65 is when people turn on their heat. So as soon as the temperature, come September, October, when summer's dwindling away, as soon as it gets to 65, people will turn on space heat. So any day, we could go through Boise, for example. So and it's always based on an average daily temperature. So you gotta take the average. So if it's a -10 is your average, that would mean that maybe you had a high of, let's say 10 degrees, and I guess a low of -20. That would be kind of how that one works. And so then you would take 65 minus your -10, and that would give you that 75 heating degree day. So yeah, and then this is our CMM. So in CMM, this is like I mentioned, just a screenshot, but it brings in our CC&B data as that demands files, and it loads our pipes. And that's kind of that spatial, it loads them spatially, exactly where they're located. That's where we want to see the demand at. Now, since we've covered this, I'm going to hand you to Zach to give a fixed network update.
Thanks, Kathleen. Yeah, I'll hop in here real quick. Yeah, we just wanted to provide a quick update on the fixed network within Idaho. Kind of relates and corresponds with what Kathleen is talking about for our synergy modeling. Currently, IGC has a goal of reaching a 90% coverage of our customer meters being read through the fixed network. Maybe I'll just provide a quick update on what the fixed network is. It's a system in place that can read meters through ERTs remotely. So the system is set up in place throughout the cities, towns, et cetera, in order to read those meters on an ongoing basis, instead of having a truck or an individual walk around and read those meters on a monthly basis. So IGC has that goal of reading 90% of our customers through customer meters. Throughout the past few years, we've been working towards that goal, and we are currently, as of Q1 of this year, at 61% coverage of reading our customer meters through that fixed network. We've had some supply chain issues over the past couple of years. Devices have been ordered in order to read the 90%, but we just have just received those devices recently and are expected to get to that 90% coverage by the end of this year, 2023. If you want to hop to the next slide there, Kathleen. Kind of how it ties into what Kathleen is talking about for synergy. We made a comparison 2 years ago in the previous IRP between the fixed network that we had at that time, the reads that we had through that, and CMM, which is those calculated loads within synergy. 2 years ago, we calculated only through 100 customers because our fixed network wasn't in place as much as it is today. But we calculated a percent difference between the fixed network loads as well as what we're seeing through CMM on a single day. And 2 years ago, we were noticing a 12% difference between those loads. We reperformed that calculation this year. Obviously have a lot more data now as our fixed network is being implemented. So you can see now this year we were able to make comparisons between quite a few more customers at 892 that you see there. And we can see that the percent difference between CMM and fixed network loads has dramatically decreased, which is a good thing there, down to 2%. So we're expecting to see that trend continue with getting that fixed network implemented to that 90%. So thanks, Kathleen.
Yeah, nice job, Zach. Yeah, but you can see, I mean, I see right here, we're getting more dialed in. So I see, I know I briefly mentioned earlier that 10% is kind of the goal. So this means our calibrated models performing very good to actual data, which is just makes us more confident in our models. And, when we ramp up to our heating degree day, which I'm going to cover right after this. But yeah, more data. I think, Zach, there was more regions too we covered. So I think in 2021, it was just Napa area, but in 2023, we did it through a couple different AOIs. So,
yeah, so 2022 was just the name.
Mm-hmm.
Yep, 2023 was all Idaho territories.
Yeah.
Thanks.
Yeah. Yeah, kind of what we're talking about. So that CMM, so the calibrated data, I'll go over this, but whenever we have this heating degree day, and this is kind of the phenomenon, you get a linear regression based on as it gets colder. So the 0 is 65. As I get colder, people, it requires more heat transfer to keep your house, set at that 70-degree temperature setting. And with this, we can go, so we try to get the coldest day to calibrate that we have in our 3-year history, because we want something recent. We don't want to go back too far. Because we've probably had, reinforcements or piping or other modifications to the system. So we always try to dial in that calibrate, and this is kind of how we ramp up to that design day, that peak heating degree day. We can extrapolate up this regression to get to that. So that's kind of how our loading works. And now, so that kind of covers our distribution system modeling process. So now I'm going to get into system deficits and constraints and kind of go through what those are, talk some terminology, and then kind of our process to address them. So we've kind of mentioned with synergy, but basically our synergy modeling, because, we spend all this time building these models, making sure they're really accurate, investing in fixed network, but we use them every day, all the time. So we look at all of our large customer requests. We model our renewable natural gas. It supports design and sizing of our pipe and pipeline components. It allows us for future planning, IRP, predicted growth, we model that out. We identify our deficiencies. We can see our system reliability and make decisions based on that. We can optimize, once we find these deficits too, we can use the models to optimize the different distribution enhancement options. I could run pipe over here, I could run pipe over here. What's the least amount of pipe that's the cheapest, compare out options, which I'll go into probably do that a little bit more. We also can look at our cold weather action plans and model curtailments. So if we do have system problems, we can it's a little predictive, or we might be able to help avoid an issue with these robust models. So now I'm going to cover what a capacity deficit is. So a deficit is defined as a critical system that is at or limiting capacity. And then I just want to talk through a couple examples of these. So it could be a pipeline bottleneck, or it could be a minimum inlet pressure to a regulator station or high pressure system. So an example of this one is, let's say I have a 500-pound high pressure system that's feeding a 200-pound system, 200 high pressure system. If my 500-pound system where it feeds the 200-pound system, let's say it has a lot of flow in it, and let's say at the end of that line, it's only at 150 pounds. I've compromised my 200-pound high pressure system. So that would be an example of a deficit. I have a compromised system. Another example might be the minimum inlet pressure to a compressor. So compressors require certain suction to meet discharge and be within the horsepower curve. So if my pipeline is losing too much pressure before the compressor, my compressor will not function correctly. So that'd be another example of a deficit. And it might also just be a physical component. This could be a regulator, a strainer, an odorizer, a compressor, just one physical component could also limit capacity. And then, with all these deficits, I just want to talk through a process a little bit, but with the IRP process, we do a comprehensive review of all of our distribution models every 2 years to ensure we can maintain reliable service during that peak low weather temperature event. And then every year with our budget cycle, we do 5-year budgeting. So we also complete system reviews on an annual basis. So we're always, we always have the option of kind of tweaking and changing and making sure, we're not missing a deficit or timing a deficit correctly. If we predict a deficit, we'll evaluate the system and recommend reinforcement and enhancement options. And then we'll select those based on alternative analysis. And then they will get placed into the budget based on the timing needs of the predicted deficit. So, and now I just want to talk a little bit more about like what options we have. Because in IGRAC 3, we're going to go through, we'll go over deficits, and then we'll also go over like alternatives. So like we got option A, B, C, why, how'd we get to selecting one of them? So a little more, but with enhancements, we always have the options typically for pipelines. We can do replacements, we can do reinforcements, we can do loops and backfeeds, we can do pressure increases and or upgrades. If a facility has a deficit, we can do a facility upgrade. Typically, we just replace the station or you could just upgrade a couple components that are needed. Another option, so if you have deficits on the distribution side, you can add regulator stations that feed the distribution system. So for us, a regulator station is always a fresh source of gas. So on a distribution system, immediately out of a regulator station, we have 60 pounds. And then that 60 pounds, as it goes out through the system, the end of the system will have less pressure, but regulator stations are kind of sources for distribution and or high pressure. Sometimes we'll have some high pressure cuts where we have high pressure feeding another high pressure. So that's an option with the backfeed too. Another option is you can add strategically placed gate stations, tying systems together, creating backfeeds. And then another option is compressor stations. And then each one of these, all our systems are unique. And so each, enhancement option, will be optimized, using different enhancement solutions. A compressor is not really feasible for a distribution system. So there's different spots for each one of these. And then I'll just give an example. Just this is a little bit more of this is just how we go through, looking at our systems and looking at options. So this is just an example. So this is basically Synergy Gas. This is one of our distribution systems. I see a couple regulators. And then you can see the source is a circle. So we see that's the gate station, kind of that high pressure lateral kind of winds down to the south. And then we have distribution. So in this system, what we're worried about is if we look at the pressure, we'll see that red area. So we have a system kind of down to the southeast that's under 10 pounds, which typically kind of triggers a concern for us. So if there's growth, that's around the metric we'd be looking at and considering reinforcing. Or maybe there's a customer that wants to come on, or maybe there's a big subdivision going on. So we know it's maybe going to get pulled down lower. So that's kind of the system we're looking at right here is, how do I address that? Click through. So we have options like a compressor station in this example is not feasible. What else? So we could look at regs. We want to make sure these regs aren't undersized or failing, that they have good pressure, to make the cut they need to distribution. So that might be something I check. I might also look into pipe. I see two spots where I could tie the system together to kind of create a loop. So let's keep looking. So one of those loops, this is why all alternatives, you got to go through them. Things could look really good in Synergy, but this one has an airport. So this would be an example of an infeasible route. I think it would be very unlikely that we could run that pipe through an airport. Let's see, so what's next? And then, so the next reinforcement option is that loop down to the south. And this is actually the model's been rerun with this loop kind of tied in. You can see it brings us above 10 pounds, which was kind of our metric for this model. So this route is feasible, no airports. So this would kind of be the solution you'd look at. So if you had that problem, that would kind of be the process some of our engineers would go through. This is a very simple example. But yeah, and something else you want to think about is we never want to overbuild. So if this development down to the south, southeast, we'd want to look at it and see, we don't want to overbuild. So that's why this is a good example. It just brings us back in to that next pressure range, because there could be, maybe there's farmland, or maybe there's some hindrance or a river or something where you couldn't have much more growth go that way. So every system, that's kind of what we look at and want to plan for, not overbuild on. You know, and things can change over time too. So with the IRP, you know, every couple years as this growth goes, we want to kind of gradually address it. So with enhancements, we briefly went through that example, but we'd always look at, and we'll cover this on every project in IGRAC 3, but we look at scope, cost, you know, what is the actual capacity increase, timing needed, system benefits, alternative analysis, and feasibility. So we touched on a couple of those things, but that would be basically how we look at projects and then choose a project. So we would do alternative analysis. So we would maybe have all these items listed out for the alternatives we look at to help us choose the best enhancement option for us. And then, yeah, so now I'll just talk, since we've covered that, I'm going to talk how to get into our budget. So typically enhancement selection guidelines include, you know, we always want the shortest segment of pipe, you know, most cost effective project, you know, most favorable construction conditions. That airport's a great example. You know, we want to minimize environmental concerns and impacts to the community. You know, we might have road moratoriums or, you know, other things like, for instance, a compressor, you have to do emissions. You know, there's just considerations you want to do. So you probably wouldn't want that in a highly populated area. You know, maybe you choose a route that has opportunity to add customers, and then always looking at cost, including restoration for the project to help us kind of choose, you know, how we select the enhancements. And then once we get to there, this slide kind of wraps up a couple slides, but this is just overall our process. And I'll just walk through, and this will lead us up to how they get into the budget. So we always look at our IRP growth, the data. You know, we have our design day models, and then we also get information from our districts, like, you know, developments, city planning, you know, maybe I know in Boise area, the S816 project I've been involved on, but, you know, just where, you know, how that's going to drive growth into certain areas. So we put all that together, and then we identify our system limitations or deficits, you know, in the models. And then once we identify those, we come up with alternatives. So we'd want a couple options on how to address them, you know, benefits, feasibility, cost, is kind of that next box. And then with that, the engineers, they'll collaboratively work with their managers and directors to review all the reinforcements, all the options, make sure we have, you know, all the options considered. And then that'll help them kind of choose a project and then rank the project based on needs. So we got, you know, with our budgeting process, lots of projects in lots of areas. So we have to really make sure we have the deficit timing right. You know, if something needs to happen this year or next year, when we budget for the 5 years, we need to make sure we're meeting those goals. So that's kind of the next box. And then it'll get scheduled into the budget. And right now we're actually right into these couple boxes because it's budgeting season. So right now for Intermountain Gas, we're currently in the capital budgeting process. So our first pass of the budget is due this June. It's in 2 weeks. And then it'll go through several iterations until it's approved, typically in late November. So that's kind of where we're at. And the next meeting, like I mentioned, IGRAC 3 will be going over our deficits on the AUIs, and then, you know, our alternatives analysis on them, and then what we're currently proposing in the budget for the 5-year budget. And then this is my last slide, and we'll just wrap up, but this kind of shows our iterative process of the IRP. So like I mentioned, every 5 years, we're looking at these projects. So projects we're looking at in this IRP, we'll look again at in the 2025 IRP. So we can always move and shift. So if growth or things change on our system, you know, or we have more development than what we thought we were going to have, you know, we can adapt and move. And with this timeline and this iterative process, it allows us enough time to plan, design, and construct these projects. And be really proactive to our system, to make sure that these deficits, basically to avoid deficits on the system. And this gives us a lot of confidence, in our system reliability. And like I mentioned, in IGRAC 3, we'll be going over those exact distribution enhancements for the 5-year budget, which is 2023 to 2028. That wraps up my presentation. We can do questions before we go to Min or take a break.
Are there any questions, any more questions for Kathleen?
Yes, this is Rick Keller with the Idaho Public Utilities Commission. Have a couple questions. Do you look at gas quality as far as BTU content on your system to make sure that you're getting the BTUs that you're paying for?
We do. So we check Williams, and I'll share a little more because this goes into a little bit of some of our renewable natural gas projects. So the majority of the time we built to Williams, except a couple areas where we take RNG gas, we have our own BTU zones and gas chromatographs out on those systems, and those customers get built specifically for that BTU. Because everyone knows RNG is a little bit lower BTU content than what we get from Williams. So they mix, and those gas chromatographs in those strategic locations allow us to accurately bill. So
okay. And then with respect to, I believe you referenced the HP laterals, and I think they operate at 60 PSI G. So do with those systems what specifies 60 PSI? Are you able to increase pressure on those lines if you have a need, or is that limited by design?
A lot of it's limited by records or original design. So the high pressure laterals are above 60 pounds. And then it depends on what they were pressure tested to, what material they are. Is kind of what would limit their MAOP is what we call them, maximum allowable operating pressure. So every pipe and IGC system has an MAOP.
Okay.
And then if you go above MAOP, that would be an uprate. So there is opportunity that we could retest a line and or file all the uprate documentation. And the uprate, you would take it up in gradual increments for, I think it's subpart K. So a little bit of opportunity, but yeah.
Okay. And then when you put in a distribution ladder, and I'm sorry for the confusion on terminology, but I'm going to say your high pressure distribution lines. Is there, I think you referenced like a 6 or 8 inch. As long as you're putting it in, do you consider? I assume you consider future growth, and so in lieu of maybe a 6 inch, that you would consider it 8 inch as long as you're putting the system in, if it makes sense for future growth.
Yeah, we got to be careful because we don't want to overbuild, and we got to be careful on the board. But yeah, you could, and sometimes IGC will pick up the cost on that, or we'll choose, like if we know, something's coming on, I guess. But yeah, we try to hit that sweet spot. So
right, as long as you're doing the construction, it seems to me that, yeah, I understand the need not to overbuild, but as long as you're considering potential future growth, and if it makes sense to put in a line that may be slightly oversized to take in, reduce the need of putting in a subsequent line later on, you are considering that, I assume.
yeah, we build out for the 5-year growth, and then some areas like Boise and Napa's 5 years growth's been pretty crazy the last couple years, and we've had a lot of reinforcements in those areas.
Okay.
But yeah, we do try. So we'll look at it typically from a sizing. So when we model out the 5-year growth, we kind of know what that load is, and then we'll, using good engineering practice, try to keep that velocity under 50 feet per second. And then,
Okay.
we could look, and sometimes we do jump sizes, or it just makes sense. A lot of times a 6 versus an 8 isn't that much more money. And sometimes Intermountain Gas will choose to invest in that like additional.
Until the demand comes on the system, then, okay. All right, well,
Yeah,
thank you.
well, yeah, you could also, you got large volume too, so they typically don't include core. So yeah, there is a little bit where, but a lot of times when large volume comes on, they, if the capacity's there, we'll give it to them. If not, they'll pay for a further enhancement. So we have to be a little careful in that we, want to be fair with everyone, because we don't want core paying for a bunch of like large volume industrial customers.
Right,
So it's like a fine balance. But yeah.
sure. Okay. All right, thank you.
Thank you, Rick. Those are great questions. And Kathleen, thank you so much. I really appreciate that. You set a really good plate for Rack 3 coming up. I learn something every time you go to this presentation, so thank you. I think next we have Men. If my lack of time is, but my inability to sense time is correct, we can move forward. Men, did you want to speak next? Did you need control, or shall I work the slides for you?
I am good with either. I could just share my screen.
Okay.
Can you see my screen?
Yes.
Yeah.
Yes.
Uh, well, is it in full screen or is it?
No, we're not seeing it in full screen yet.
I think you gotta put it on your other screen, man.
Yeah.
Share something.
Okay. Is it full screen now?
No.
It's a little small. Do you have it blown up
Yeah.
like in your full window, I guess? Do you have it in maybe a smaller window?
I have a vertical window.
Yeah, it's showing the vertical window.
Yeah.
Mark, could you just share yours? And
No problem. No problem.
sorry about that.
One moment here.
Sweet. Thank you.
You're welcome, sir.
So hi everyone, I'm Min Park and I'm going to be going over avoided cost methodology today. So a brief history about avoided cost. For those of you that were at the last IGRAC 2 meeting a couple of years ago, this is going to be a lot of the same stuff. But in 2019, IGC was asked by commission to take another look at our avoided cost calculations. At the time, the program was a couple of years old, so they were looking for an upgrade to the analysis and a more detailed look into other potential costs for just overview and review process. In compliance in 2020, we asked members of the Energy Efficiency Stakeholder Committee, which is a group of stakeholders and experts in the community that have some sort of interest in our energy efficiency program. And they formed an avoided cost subcommittee to tackle this specific concern. And the committee met and came up with an agreed upon interim model that we have been using ever since. So the subcommittee met again in March of 2022, and we couldn't agree on a distribution cost, so that number is still set at 0. And so what is avoided cost? Avoided cost in a nutshell is just meant to put a dollar value on to energy savings. It's sort of like if you were to do this calculation at home and you were considering upgrading your appliance to a higher efficiency one. The way you would think about it is in terms of like how many gas or therms can you save in a year by upgrading to this appliance. And then you would look up like how much you're paying for that gas. With the two numbers that you come up with, you would then put a dollar value on how much you're saving in a year. And in principle, that's the same thing that we're calculating, except instead of one appliance, we're looking at a large number of appliances through rebate programs or other therm savings through education and all different types of measures. This is useful for IRP purposes because it allows us to look for opportunities where energy efficiency is in fact more cost effective than the supply side option. On top of that, it allows us to compare those measures to find out which ones will produce the most therm savings for the same or lowest cost. If you could go to the next slide. So the natural gas supply chain, like I mentioned earlier when I talked about like upgrading to higher efficiency appliances, you would also look at how much you were paying for gas. And to do that, you would look at your gas bills, or you could find the tariffs online. But being a distribution company, our cost component is a bit different. In fact, there's a lot of costs along the way. We would fall somewhere on the end of that flow chart in the orange with the distribution. The first part is called commodity cost, which is just the cost of the gas molecules themselves. So the actual gas as an item. Transportation costs, which are the costs associated with getting gas to our city gateways. And finally, there's a distribution cost component, which consists of the costs required to accommodate the extra therm of gas in our distribution system. And you could go to the next slide. So this is the formula, broken down into like a math formula. Put simply, the nominal avoided cost per therm is the sum of those three components we just went over, commodity cost, transportation, and distribution cost. It's pretty important that we look at this in nominal terms, at least to start off with. And the reason being that we're looking at therm savings that happen over a number of years. sometimes as many as 20 to 25 years of therm savings. So we need to evaluate those, and then we put them into real dollars and finally apply a discount rate conversion. And then if you could go to the next slide. So commodity cost, we'll be going over how to calculate each component individually. The commodity cost represents the purchase price of the natural gas molecules that the company does not need to buy due to therm savings. It varies depending on which one we're talking about. Like for the commodity cost, there's a lot of factors that can influence the price we're paying for gas. It depends on factors such as where we're purchasing from, the time of the year, demand, the season. There are day-to-day fluctuations when it comes to this, so it makes it a bit tricky to pin down. So how our calculation starts is we use a internally produced 30-year price forecast for the 3 primary basins that we purchase from, and we apply a first transformation to that forecast, which is a weighting based on day gas purchase data, which uses actual company data where we purchased daily spot gas in the past and applies that towards the forecast of the future. And finally, there's a heating degree day shaping process, which is used to account for the seasonality of the prices and the therm savings. And next slide. And then we have transportation cost. This is the cost associated with getting the molecules of gas to the city gateway. This is composed of the cost of reserving capacity on the Northwest Pipeline. So those are costs that are very well outlined in our PGA, or purchase gas adjustments. We use those numbers and figures along with the volumes and rates to actually come up with the transportation cost, or at least that component of it. There's small variable portion cost, which is admin and other fees on a per therm basis to transport to the city gate. And lastly, distribution cost calculation. The general concept here is that through energy efficiency, we can delay or avoid costly pipeline capacity expansions, and it allows using existing infrastructure in a more efficient manner. However, this is probably the most difficult portion to calculate because those large expansions, they occur pretty irregularly, which makes it hard to generalize those cost savings to any one particular therm that happens in any moment or place in the service territory. Currently, like I mentioned earlier, the calculation for this has a value of 0 at the moment. And as part of this IRP process, we're going to be working with stakeholders to try to develop a distribution system cost. And lastly, these are some of the updates for the 2023 IRP. They're pretty in line with the last IRP we did. So things such as like updating basin price forecast, heating degree day shaping, new year of day gas purchase data, updated transportation cost with the latest PJ tariff are all things we did previously. The one thing we did update was the inflation rate, which was at 2% and now it's at 3.15%. I believe we used a 5-year average to come up with our inflation rate. And does anyone have any questions?
Yeah, man, this is Taylor Thomas with the Idaho Public Utilities Commission. In regards to the inflation rate, has that historically been something you guys have used in your calculation?
Yes, we've for previous avoided cost calculations, we've used 2% inflation rate, and it's just an updated inflation rate based off a 5-year average. So with last year's inflation rates, it bumped the number up quite significantly.
And do you apply that overall to the entirety of the calculation or to the commodity or just transportation?
So the inflation rate is used for the, I believe we use it heavily for the commodity cost portion.
Okay.
Jason, you have your hand up.
Yeah, I do. Thank you. Real quick here. I noticed on your table on the last slide that your previous costs were all very even for the most part, a 1 cent increase in 2026. But for your updated costs, there's quite a lot of variability, going up and down between 80 cents to $1.27. Could you just explain what of these updates or what is driving that change from a very regular to a variable cost?
Yeah, so those numbers are based off our gas prices by year, and the gas prices by year are just, like I mentioned, heating degree day weight factors. So it's the weighted price that the prices that I have are given to me through a price forecast, and then they're weighted through give me a second. They're weighted based off heating degree day shaping. So with the shaping being this year's shaping percentages, and then we take those numbers, and with that we get the cost, which for 2023, and I think there was a big bump with the inflation rates and with our gas prices being pretty high in the early part of this year.
Okay, I think that answers maybe some of my question, but not all of it. Because my understanding is that gas prices always have some variability. There's always some up and some down. Um, it's kind of I would expect to see if gas prices are up and down, even in the previous cost, there would be some following. But it sounds like there may have been a change in how the heating degree days are used to shape that. Is that driving that change?
I would say that, well, our heating degree days are pretty, so it's heating degree day shaping, they're weighted for months. So I would have to see how it compares to the 2021 numbers, but I don't think there was a big difference. I think the big difference came in the gas prices that we paid, or how high the gas prices were early on this year, and all the price adjustments that we had.
Excuse me, man. This is Mark. Jason, maybe I can help provide a little context there. Prices. As you know, we had a bit of a wacky winter with weather, and that caused some enormous variability in gas prices. Unfortunately, I can't speak to the static numbers that you're seeing for the prior IRP. We can look into that and provide some more explanation about why that difference. But I would assume, again, basically what Min's saying is because we saw volatility in prices in December and January because we had such unexpected weather events, that has contributed to that pricing volatility that you're seeing there. Again, for the previous IRP, we'll need to take a closer look at that, but we will report back to that to this group either via email or through at the next RAC meeting.
Okay, yeah, I think that would be great. Thank you.
Mark,
Yes.
this is Kevin.
Hi, Kevin.
Pete. So one thing that might be helpful would be the work papers behind the calculations, and then we
Mhm.
can walk the numbers through and understand what it means.
Good point. We'll provide that.
And then I just have one more follow-up. You said for the distribution costs, you're gonna work with stakeholders. What exactly do you mean by that? Are you gonna work with the avoided cost subcommittee, or are you working with the stakeholders in the IRP?
That I'm not sure. I was just told that we would be working with stakeholders to come up with a new number.
And
I guess I would have a bunch more questions as to what that is. Is it Intermountain Gas gonna propose a new model? I mean, in the past, we have met to discuss this. We haven't come to any resolution, so I guess would it be Intermountain Gas proposing a new model or number? Do that, or asking the stakeholders to come up with a new number?
I think it would be Intermountain presenting, walking through the calculation and soliciting feedback on to determine whether that's an acceptable approach. So it would be between basically this larger IRP group. We would set up a workshop or as part of the discussion at the next RAC.
Okay.
Mark, Kevin again.
Hi,
Maybe I can expand on Taylor's question. I think I understood what he was asking, is that there are multiple stakeholder committees. So there's the IRP stakeholder committee, there's the energy efficiency stakeholder committee, and then there is a subcommittee of that energy efficiency stakeholder committee to address avoided cost. So I think maybe the question Taylor was asking is, which one of those forums,
Oh,
or
I
is
see.
there a mix of those forums that are going to address the distribution component of avoided cost?
From the avoided
Taylor,
cost
did I get
perspective,
that right? I don't want to put words in your mouth, but
Yeah, that's correct. You just say stakeholders, and I wasn't sure if it's applying to this group because we had a
okay.
group that goes over that, but I'm open to
Yeah.
having more stakeholders, and I just want to know how you plan to address that.
So and forgive me, that usually has happened with the energy efficiency subgroup in the
Yeah.
past. Is that
This is
okay?
Kathy. I think that we
Thank you,
would
Kathy.
probably continue working with the avoided cost subcommittee, where we have the history of kind of where that discussion has been and where it's going, but certainly would welcome including the IRP stakeholder group, in developing something. So yeah, I think we would continue with the process that in the way that we have been, but certainly open to other ideas if there are any. Does that help?
Oh,
Yeah,
that
that
helps.
helps.
That helps me, Kathy.
Okay.
Thank you. 'Cause
Okay.
I wasn't
I
sure
think that's
myself.
reasonable.
Okay.
The other thing I would peg for that group to discuss is the inclusion of the inflation rate here. That comes as a little bit of a surprise to me. Going through previous calculations, that's not really something I've seen. So I would peg that as a discussion point in the future.
Is that Taylor?
Yes, that's correct.
Okay.
That's Taylor.
Great. Okay. I will make a note that we will cover how that's been applied in the past and discussion for going forward.
Thank you.
Excellent. Thank you. Sorry to jump in there.
Oh no, thank you, Kathy. This is my first go around. It's part of the process. Are there any other questions? From otherwise, we will move on. Okay. Up next, Kathy.
All right. Great. Mark, if you don't mind continuing to drive the slide deck, that would be awesome.
I will do my best not to steer us into any brick walls.
Appreciate it. Excellent. All right. Well, thanks everyone for the time this morning. I'm going to talk a little bit about our energy efficiency program and more specifically about the conservation potential assessment used to feed the IRP. We'll go ahead on to the next slide. And so Min's done a really great job of kind of setting us up here and explaining a lot of the role of avoided costs in here. But the official description of demand side management, it refers to the resources acquired through the reduction of natural gas consumption due to increases in energy efficiency, increases in efficiency of energy use. And so when we're thinking about energy efficiency, we're really kind of thinking about what is that reduction of consumption due to energy efficiency. I think Min did a great job of explaining this, that, we have the option of going out and purchasing supply from the market in option A, or option B, we can purchase that supply back from our customers in the form of energy efficiency. And you can kind of see the dollar amounts there to sort of represent the cost-effective energy savings is what we want to secure. And so we will apply the utility cost test to make sure that the energy savings are cost effective and that we are indeed doing better by doing energy efficiency than going out and purchasing in the market. So that's the role of avoided cost comes into that calculation to make sure that we are securing cost effective therm savings. And since I have an audience, I'm of course going to make a shameless plug for all of our current rebate offerings just to make sure that everyone's aware of any energy saving opportunities that they may have an opportunity to take advantage of. This is a list of our residential rebates that are available right now. You can find all of this on our website. We also have applications available on our website, but this is our most recent offering for our residential customers. We also have a new construction program that is primarily for builders. It's a 2-tier program, which requires the home to be HERS rated. And then there's some very specific energy performance targets that need to be met in order to qualify for the rebate. But we are offering 2 tiers there for new construction of residential homes. And then in addition to the new construction rebate, this is new since we implemented this offering, but we allow builders to also stack on rebates for a smart thermostat and also for water heating, which is not included in the performance targets of the new construction program. I see a couple questions. Yes, please.
Kathy, Kevin, for those on the line that don't understand what a HERS rating is, could you give a brief overview?
Absolutely. Great. Thank you. So the HERS is a home energy rating system. And what happens is when the home is constructed, they work with a official third-party independent certified rater, and the rater will come into the home and they performance test the home. So they're looking at all the things like high efficient appliances, they're looking at air change per hour, they're measuring duct leakage. Really, it's a way to measure the energy performance of the home, and the home is given a score. So a standard code-based home is typically a score of 100. For an energy efficient home that scores at a 60, that means that the home is approximately 40% more efficient than a code-based home. So we don't have a HERS threshold, but we do use the HERS rating because when a home is HERS rated, they are also checking all the performance targets that we want to set a level for. So air change per hour, duct leakage, furnace efficiency, those are all things that are already measured when your home is HERS scored. So we're leveraging that certified system in order to measure the things that we want to capture. Does that help?
Thank you.
All right.
I understand what they are, so I'm not sure
Yes.
if others that have not been exposed, if that explanation makes sense. So I would encourage folks to, if they have
Yes.
additional questions on that, to please ask.
Thank you. I am guilty of getting into our acronyms and EE speak. So do call me out and stop me anytime you have a question. I appreciate that. Yeah, a couple more questions. Jason.
Sure, thank you. I had a question specifically over that new option. This may not fit here, so if that's maybe a better place to discuss, that's fine. I just don't remember seeing this in the last energy efficiency subcommittee. But my question was on the stack of the whole home and the smart thermostat.
Mhm.
Those both deal with the same technology of the furnace, the HVAC system.
Mhm.
I'm wondering how you might have accounted for the overlap of, a high efficiency furnace that is also being used less because of the smart thermostat.
Ooh, that's a good question. I will have to go back and look at that. I don't have that off the top of my head, but I'm happy to follow up on that.
Yeah, I'd appreciate some follow up there. Thank you.
Okay,
Carry on.
yeah, thanks. Any more hands? Kevin, did you have another question or you have residual hand up?
No, so it's another nemesis, mute buttons
Oh.
and hand raised.
I am also guilty of that. So no, I appreciate it. I just want to make sure I capture questions. So thank
Thank
you.
you, Kathy.
Sure. All right. Next slide. Okay, and then April 2021, we also launched our first ever commercial energy efficiency program. So we have a modest offering here, learning a lot about our commercial customers, but we offer heating incentives for commercial folks, and then we're also offering incentives on commercial kitchen equipment, so all of the Energy Star equipment. So great. Okay, so we'll move on to the CPA here. We have been working with Guidehouse on our 2023 Conservation Potential Assessment. So I am borrowing some slides from their presentation to present the results of the study here. So you'll see their Guidehouse logo on there. And this is the Guidehouse team that we've been working with throughout this process. And this team did present to the Energy Efficiency Stakeholder Committee. So some of you might have been through this before, but we'll run through it and make sure everyone is aware of the how we use the CPA. So what are the objectives for the CPA? Estimate achievable natural gas energy efficiency potential within the IGC service territory, forecast net impacts, and we're looking at a 20-year period here for the CPA from 2024 to 2044. And then we'll use these results to inform IGC's energy efficiency goals, portfolio planning, and budget setting, and then also to contribute to the IRP process. So identifying what kind of potential savings are out there, and then also use it for program planning. What are some new saving opportunities that the program can leverage? Okay, we'll jump into the methodology that was used by Guidehouse. Okay, so conservation potential assessment really identifies 3 different kinds of potential, and that's kind of shown here with this funnel. So the top level is technical potential, and you can really think about this potential as sort of magic wand potential. So if we were to magically be able to make everything energy efficient today, adopted by all customers, used and available and implemented, this is the technical potential that would be available. And so we, as I mentioned before, we're really only interested in cost-effective savings. So at this point, we start putting on some layers to the technical potential, and we say, okay, we really want to look at the economic potential, which is the cost effectiveness screen. So we're going to screen the potential by the utility cost test, which is used by the Energy Efficiency Program. And so now we're going to look at, okay, these are all the things that are cost effective that we could implement and the savings that we could get. And then finally, we look at achievable potential. And this is where we'll kind of dive in a little bit more here. So achievable potential is really customized for the Intermountain Gas service territory, customer growth, equipment that is available in our region, adoption levels. It's really looking at a lot of different factors that will customize down to Intermountain Gas to say, okay, here's what's achievable in your region for your customers that's cost effective. And so we're going to look a little bit more at that. Great. Okay, so this is kind of what I was explaining. I forgot my next slide. So calculating the market share, penetration of measures, customer awareness, customer willingness to adopt, looking at payback times, calibrating forecasts using historic program data. So these are all the things that kind of went into that achievable potential to make it specific to Intermountain Gas. Okay. So here we have a chart that shows the cumulative net achievable potential by sector. You can see the greatest potential there lies with the residential sector. Commercial sector is much less. And then we have the total natural gas cumulative potential as a percent of forecasted natural gas sales. So you can see we're not getting out to about 7% until 2044 of what we identified as potential savings from the energy efficiency program. Again, showing by sector, residential versus commercial sector. This shows where we can secure those savings. So within the residential program, the largest portion of potential savings come from HVAC, so furnace, boilers, combi boilers, and then we have our other sectors or other measures there, hot water measures, envelope measures, and then finally appliances. This is a similar view of where savings will come from or have been identified to be able to come from in the business sectors by the different areas, retail, office, lodging, light converted, healthcare. So this gives us an idea of which customers can contribute to those potential savings over the time period. And so those charts that we were looking at were all really what we'd consider our base case or our business as usual. Business as usual means that budgets stay about the same, customer awareness and willingness stays about the same. And so that's kind of the savings potential if we were to change nothing else and just continue on with business as usual. And so when we looked at the achievable potential, we also had the opportunity to run a couple of different scenarios and change some of those inputs and say, we did the unconstrained historical budget, we did a medium adoption and a high adoption, high incentive. So we took the business as usual base case and we took off the budget constraints of the historical program and said, okay, so if we increase the budget, if we impact that by increased activity, we increase awareness and adoption, what would that scenario look like? For the medium adoption, we assumed things like, we'd had an influx of people moving into Idaho, potentially coming from areas that have more awareness about energy efficiency. Those customers may be more likely to adopt. So, we have a higher customer awareness and a higher willingness to adopt. What would that scenario look like? And then finally, we ran a third scenario saying, okay, let's say we increase the budget, we increase activity, and we have this high awareness and high willingness. So now we've got high scenario. How does that impact potential third savings? And this is what that looks like. So you can see the red line is the high situation where we have high adoption, high activity, high incentives. We've increased activities and we've got the highest kind of therm saving potential scenario there. The gray line is medium adoption. And the green dotted line is our unconstrained historic budget where we increase some budgets, we increase activities, we impact awareness and willingness to adopt. And then the low blue line there is a business as usual. So we change nothing, we continue on as we are, and we can consider adoption and awareness to say at about the same level. And then finally, we have a chart here demonstrating all of the technical, economic, and then achievable potential and the 4 scenarios that we ran in order to take a look at how could we impact savings and what might that look like. Kevin.
So those are not measured against the UCT. That's blue sky, go get it if you could do it. Is that safe to say?
Of the 4 scenarios that we ran?
Yes.
They are still considering cost effectiveness. Yes, they are.
Okay.
In the achievable potential, those all take into consideration that they are cost effective savings, that they have passed the UCT test.
Thank you.
Yeah. Other questions?
Sure, I'll jump in on a question here.
Absolutely.
For this slide we're on, has the technical potential and the economic potential listed, but I didn't see the achievable line, is that wrapped up in another line somewhere, or
Right.
how does
So
that compare?
on this chart here that we're looking at, the bottom 4 lines are really all part of the achievable potential. But within that achievable potential, we ran different scenarios. So the bottom
Okay.
line there is the business as usual. And then we looked at things like increased budget, increased awareness, increased budgets and awareness. And so that just allowed us to kind of play around with what if scenarios. What if we did this? How would that impact savings? Does that help?
Yeah, that answers it perfectly. Thank you.
All right, great. Okay, any other questions? Taylor, yeah.
I might have missed it, but I guess for the modeling and the base case for the company's IRP perspective, which one of these are you planning to use?
I think that's a great question. And I've been talking with Brian and the resource planning team. I think that, our most conservative approach would probably be to use business as usual. But where the CPA has identified some new therm saving opportunities, new equipment, higher efficient equipment, I think that is to be determined by the resource planning group and certainly the stakeholder committee on which is the most appropriate to use for IRP planning.
Okay, thank you.
Yeah, I'll chime
Yeah.
in a little bit. So
Yeah,
with
Kathleen.
distribution system modeling, because we pull our data and rebuild our model. So if we predict like more, DSM, I guess, demand side management, whether we see that or not, it would be in our next, cycle, I guess, kind of that iterative process we talked about. So every 5 years or, when we reassess, and apply the growth, we can kind of change and adapt to that.
Right, no, I understand that, but you still need one for your ultimate preferred portfolio that you're going to choose. So I guess that's the kind of the question I'm asking is, what is the base case? I know that iterative process, if you kind of update as you go and you learn which one might be best, but trying to figure out what might be used for preferred portfolio.
Right.
Okay, I'll jump in with another question here. For the unconstrained historical budget, you mentioned that it's just removing the cap of historical and what that has been, and you increase your spending. But I wanted to ask on what is now that you've uncapped it,
Mhm.
how are you capping it again? Is I guess the question of you've removed that cap, but you still have some sort of upper limit to keep that, I suppose reasonable. And how is that kind of worked in?
Right. Let me see if I can. Okay. Um, let's see here. I may have to revisit the Guidehouse's technical report on this, but this one uses the unconstrained historical budget uses a ramped up adoption, driven by increased activity. It's at a certain point when your budgets are too high, then things become not cost effective. So we're making sure that everything that's in there is cost effective. And this is using an incentive level of like 50% of the incremental cost on the unconstrained historical budget. Does that help? And I can dive more into that
I
and
think
circle back.
that might cover it if it's 50% of the 50% of the incremental cost for the incentives,
Yes.
and it's by ramp up. I think that sounds like it would be you just increase those, and that's where it increased to, and I think that works for me.
Yes. So Guidehouse has some industry standard like ramp rates and adoption rates that they use, and they adjust those levers within the model. So these results were all produced by Guidehouse using the model. We haven't, Intermountain Gas, we ourselves have not done any tinkering. So this is all coming from Guidehouse.
Thank you.
Yeah.
So if you're setting it at 50% incentives, is that not considering cost effectiveness?
No, it is. These would still be cost effective, all cost effective energy savings.
Okay.
Other questions? I think my next slide was just for questions, so.
I think I have one last one, mostly for
Yeah.
the sake of my understanding, but I
Sure.
just saw Kevin raise his hand and I don't want to dominate the time.
I welcome
Go
any
ahead,
and all
Jason.
questions.
Okay, all right. Let it be known I tried to be nice. I wanted to return to slide, I believe it was 65, the achievable potential for commercial customers. You mentioned that it's lower than residential.
Mhm.
But to my mind, as it increases, 1 million therms per year is still a large number. So I guess I'm looking for a little bit more context of uh, from the view of Intermountain Gas, what's a lot of therm savings, what's a little, how did this graph translate?
In terms of like the commercial, identifying the commercial potential savings.
Yeah, so, from a utility perspective for these commercial savings, let's, just keep it nice and simple. In 2040, it's about 1 million therms. How does
Mhm.
that compare in volume of savings? Is that a lot of savings? Is that still a fairly small amount, all things considered?
That's a good question, Jason. I'd have to say all savings are good savings, right? No, that's a good question. I think that in terms of our commercial program, I might have to say I don't know. That program is so early in development, and I guess I would say it feels small relative to our residential savings potential. And we have a pretty modest, appliance or equipment program in the commercial uh, savings potential. Um, something that we look at is that, to really secure um, savings from the commercial side, we're probably going to have to look at more of a custom type program, a project by project type program. Because it does feel like just an appliance or just an equipment replacement type program is pretty low compared to what residential potential is.
Okay, yeah, I think that
Uh,
works. Thank you.
Okay.
Kathy?
Yes.
So yeah, back to those slides. When we're looking
Yeah.
at them and we say that those are based on being cost effective. So when we say that, what avoided cost? The currently approved avoided cost or the avoided cost as proposed in the previous slides?
So these are the avoided costs that we got from the resource planning team. So I would say the avoided costs that
Okay.
Min was going over. So yes,
Yep.
updated
Thank you.
avoided cost. Yes. Thanks for pointing that out. Any
Are
other
there any
questions?
other Kathy's?
Great. All right. Thanks, everyone.
Thank you, Kathy, and thank you again, man. We got about 30 more slides to go, so I suggest that we take a short break for we'll take a quick 10-minute break, come back, and we will finish up. So we'll come back at the 10:50, and we'll see you all back then at that time. Thank you. Hello again, everyone. We're back, and we're ready to continue on with the remaining present portions of the presentation. Up next is supply and delivery resources, and I believe that would be Mr. Eric Wood. Eric, do you need me to run the slides for you, or did you want to take control?
Yeah, go ahead, Mark. It's fine if you run them, and that way I won't mess it up. Maybe.
You're trusting me to drive? I'm not so sure that's a good idea. Here we go.
Okay, my name is Eric Wood. I'm Supervisor of Gas Supply for Intermountain, and I'll just talk briefly about our traditional kind of supply and delivery resources that we have to get gas to our system. Here it goes. Took a minute. So gas supply planning, kind of what is our goal? Is to meet the energy needs and expectations of our customers. Of course, reliability, 365 days a year. Security, delivery on the coldest day. There's a lot that goes into that during the winter to deliver all that gas on the coldest day. And of course, we want to do competitive and stable pricing, and we do that through a mix of fixed price hedges and storage as well. And then we want to meet future growth, and we frequently evaluate the portfolio. So that basically includes a yearly planning process, a monthly planning process, a weekly, and even down to the daily level. So what are traditional supply resources? So natural gas supply is the molecules or the commodity that's actually delivered to our system. And we do that through interstate pipeline capacity, and then also storage facility capacity. And then we throw in energy efficiency that Kathy talked about. Non-traditional resources. So right now, Intermountain does have a few renewable natural gas projects on our system that's delivered gas to our system. And then we'll look at hydrogen possibility in the future of delivering hydrogen mix on our system as well. So where's that gas come from? Typically here in the Northwest, most of our gas comes out of Canada, more specifically for Intermountain because of the capacity arrangements that they have. About 90% comes out of Canada. And so some of that comes from British Columbia in the Western Canadian sedimentary basin, and then the other portion comes from Alberta in the ACO region. And then we still do get some supply out of the Rockies, Wyoming, Colorado, Utah. So access is dependent upon the available transport capacity, as I mentioned. So it really changes in terms of how our transport capacity changes as to where we're sourcing that gas from. This is just a quick look at the North American gas plays, just gives you an idea where most of that is. As you can see in the West, we're really dependent upon the rest of the country and Canada to import those gas supplies into the region. Forecast observations. So I'll show a slide here in a minute, but there's been an increase in shale gas production over time, and that kind of started occurring in about 2008. And so there's still plenty of supply due to that shale production. We have a lot of mature basins, like I mentioned, the Western Canadian Sedimentary Basin, the Gulf on and offshore. And so there's still ample supply in the country and in Canada to meet supply versus demand. And this is kind of a quick look at production by play. It just kind of gives you an example of kind of what's occurred in those natural gas plays from 2008 forward up to 2023. And so some of those have played a much bigger part and role, especially the Marcellus. Of course, we don't really source gas from Marcellus, but it just gives you an idea of where some of that gas's increase has come from. And then this is kind of history versus projections in terms of like the use. So we do have quite a few transportation customers on our system, but this is overall Electric power is still, a big consumer of natural gas, and then consumer residential, not quite as much. Industrial and liquefaction. Liquefaction gets more and more all the time. As you've seen in the news, the liquefaction plants where we're exporting gas to Europe to support Europe. So that gets to be more and more all the time. I suspect that that's going to keep going in the future. So it just kind of gives you a quick example of consumption by sector. So our supplies, so natural gas is a commodity, of course, and the market is liquid, and we buy gas at those liquid points that we can. And the price follows supply and demand fundamentals. And there's a lot that goes into that. It can have, fundamentals can have, prices can have an effect when, some of those things are out of whack, like transportation constraints can have a big impact. Storage can have a big impact, and of course, cold weather, has a huge impact every winter, and how the winter shapes up. And so we'll look at price history and forecast.
Real quick, it looks like we have a question.
Oh, sorry. Yes, Rick.
Yes, could you go back 2 slides, please? So there on the lower right corner, it says lease and plant other. Could you explain what that is, please?
I'm not sure exactly what that is. I got this off of EIA, and this is an older slide, and the EIA, they don't actually include this any longer. So I'd have to dig more into that, what that lease and plant is.
Okay, thank you.
This is just a longer term look at some pricing over time with Sumas Rockies and ACO, which is where we base our pricing on here in the Northwest. And it just gives you kind of a look at different things that may have occurred in the West and how pricing can affect that. Even when you look back to 2000, you had this big cold period, and so pricing really spiked back then. And then you can have various things like the polar vortex in 14. We had a little bit of price spike then as well. Next. And this looks like a really flat price curve, but it's actually really not. This is from November 16 to May 23. It's just that this last winter, we had this huge price spike in Rockies and Sumas, and that is shown on the right-hand side of the graph there, and that really had to do with a lot of different things, but the winter was really cold, for example, from kind of like late November through the first few weeks of January. There was a lot of low storage going into winter as well, and storage was really used up and depleted by the time January came along. And then there was also some pipeline constraints going into California that kind of affected the market in the Northwest as well. So regionally, we can have a lot of different things that affect pricing. And then I'll let Jenny talk a little bit about the forecast. The resource planning team does the forecast moving forward, so I'll let her talk about the next couple of slides.
All right. So Intermountain's IRP price forecast is a long-term planning price forecast based on the blend of current pricing and long-term fundamental pricing. The fundamental forecasts include sources from Wood Mackenzie, EIA, the Northwest Power and Conservation Council, BenTech, and the Financial Forecast Center for long-term prices. These are weighted from the sources based on historical performance beginning in year 2 of the forecast. Year 1 of the forecast is determined from Henry Hub NYMEX. That's completely 100% of the forecast for the first year, and then it's interpolated along with the rest for the following years of the forecast. Intermountain is gathering renewable natural gas information and plans to model RNG as a potential resource in the upstream optimization process. And then you can see here, based on this graph, this is price forecast. The blue is Sumis, red is Rockies, green is ACO, and then yellow is that weighted price. And these are weighted based on where we source our natural gas. So that 80% comes from ACO, 10% from Rockies, and 10% from Sumis. I'll throw it back to Eric.
So this will be a look at our transportation and storage resources. So obviously we have to get that gas to our system. And so Intermountain holds long-term contracts on 4 pipelines. So 2 of those are Canadian upstream pipelines, and then 2 are in the US. And then of course, all of our gas is directly delivered to Intermountain through the Williams system once it gets here. We just have to depend on those upstream pipelines in order to get that gas to the Williams system. And then the capacity on Northwest is determined both at receipt and delivery points. So each contract has specific amounts of receipt and delivery. And this is so delivery to Intermountain service territory is held by firm capacity delivered by Intermountain. We can also do what we would call city gate delivery, where we have deals with suppliers while they deliver it directly to our city gate, for example, like Boise here. So we don't have to use upstream capacity to do that. We also do things like capacity segmentation, and Intermountain does a lot of that, where they have a longer path contract and they'll segment it, release a portion of that contract, and use maybe only the other portion of the contract to mitigate costs. And then the market forces drive new capacity projects, of course, and the need for new capacity. This is just a quick look at the Northwest, of course, Boise, and most of Intermountain service territory sits right on the pipeline. And then we take our gas off at Stanfield, Oregon from GTN. And then upstream of GTN are Nova and Foothills, and those are the 2 Canadian upstream pipelines that we gather gas from in Canada. Just a quick look at capacity resources that we have currently. Through the help of our AMA, IGI, they're always planning capacity, and so they're always looking at upstream capacity, and we provide them forecasts with what we'll need in order to meet demand. So what is storage? Of course, storage is a couple different things. We store gas in natural man-made structures. Those are where that gas can be injected. The 2 of those types of storage are at JP and Clay Basin. It's injected over longer periods, lower periods of demand and lower prices. So summertime, in other words, inject in the summer, withdraw in the winter, in order to meet that higher demand. And storage does act somewhat as a hedge as well.
Real quick, it looks like we have another question.
Oh, sure, Kevin. Sorry, I get so focused on looking at the information.
So what is the business arrangement with Jackson, Prairie, and Opal? Do you just buy capacity, or have you got ownership in those facilities, or how does that work?
No, those are all leased. Yeah, so Jackson Prairie and Clay Basin are leased storage, and so we just pay an amount for that leased storage.
Thank you.
Yep. So this, why we need storage, obviously, our demand's not linear. Summertime, we're down in the 35,000 range, and in wintertime, we can be as much as 380,000 decatherms a day during the peak time. So it's very much not linear. So transport capacity is very linear, however, and when we buy that transport capacity, it's all year long at a specific amount. And so it's not feasible to meet peak demand with only interstate capacity, and that's why we use storage. And so storage definitely enhances the winter and peak deliverability capability. It does minimize our cost too, because that's part of the hedge, I guess you would say, that we're injecting that gas in the summer. And then it flattens out the balancing need with seasonal demands as well. This is kind of a visual example of what I just described. And so that line in the middle basically is our transport capacity. And then over on the right-hand side with the red, you can see that's where our demand really drops down and we're injecting into storage. And then in the green, that's where we would be withdrawing from storage in the winter. And so we utilize storage around those timeframes in order to make sure that we balance our system. So the uses for storage, like we've talked about, needle peaking. So to meet those really high demand loads where we don't necessarily always have to use all the transport resources that we have. We use storage also as a winter base load, and we have a storage curve where we would draw kind of a base loaded amount depending upon the month out of storage. And then also we use it for day-to-day load balancing. So if the amount drops below that or is above that, we can either pull or re-inject storage accordingly in order to balance the system out accordingly, because wintertime, the fluctuations are much greater than summer. And then we use it, as a price hedge, like I've talked about. And then system integrity and emergency issues, we've had different issues come up regionally over the time where we'll have to withdraw more storage and even sometimes into our system. So two types that I've talked about.
Excuse me, Eric, I'm sorry.
Oh,
Like, we
sure.
have a question.
Oh, sure. Sorry about that. Go ahead.
Thank you. With respect to needle peaking and associated with your storage, so how does that work with transport capacity on the transmission system? It almost seems like it would compete. Could you maybe provide a little more detail associated with needle peaking?
Yes, sure. So typically needle peaking, we would use LNG. And LNG does come with specific transport contracts that are storage redelivery contracts, TF2 contracts. And so those are kind of separate from our other resources that we have. And JP also has TF2 contracts that are separate from our other transportation contracts. So that's kind of what we would say needle peaking. When we use those storage contracts, we pull gas out of storage. Needle peaking, like really high days, we would use LNG typically because we can withdraw greater amounts more quickly. And those contracts with the liquefied storage have a higher capacity on those TF2 contracts. So it's kind of separate somewhat from our other normal capacity that we have on the pipeline. Hopefully that helps.
Well, I think it helps me understand with respect to the LNG, and I mean that's near your load, I would think, right? As I understand your LNG facilities, and so it doesn't utilize as much of your Williams transport capacity during those peak periods. Is that a reasonable understanding?
It's not really that it doesn't, well, it just uses a separate contract that's only associated with storage.
Okay.
So it doesn't use up our other normal transportation resources. So some of those are tied directly to a specific contract that gets that storage gas to our system.
Okay.
And it's not a matter of length. It's just a matter of that we have specific contracts that are really tied just to storage.
All right, thank you.
Yeah. Sure. And like I said, liquefied natural gas and underground. The liquefied natural gas that we have is at Plymouth, Washington. And then also we have liquefied natural gas in Nampa here that is actually behind our gate on the system. And then the underground facilities would be the Clay Basin, which is down in Utah, and then Jackson Prairie, which is in Washington.
Thank you.
Kathleen, but we also have LNG on Rexburg LNG. We have a couple LNG tanks that we refill often at the Napa LNG plant.
Yes.
To help support high flow in the Idaho Falls lateral.
Yeah, sorry about that, Kathleen. I forget about that one sometimes, but yes, that one does push gas basically back down, so it kind of reduces load that's needed to on the compressor, number one, to push that up the lateral and to get that gas down the lateral. So it does support that lateral.
No compressor yet on the Idaho Falls lateral, but
Oh, sorry, that I'm thinking of Sun Valley, but yeah, sorry about that. Yeah,
it's okay. Yeah, it helps for peaking. So that peak day, it helps us boost pressures, helps the line recover. It's kind of a supplemental source for us, down the middle of the line.
Yeah.
So and I apologize, the LNG plant not located in Nampa. So do they if it's an LNG plant, do they vaporize it and then send it in the same transport line as you do with your normal natural gas, or is it a separate line?
Yes, they do that at Plymouth, and we also do that same operation at the Napa LNG. So our Napa LNG plant's tied into our Napa gate. So it can also help the, I guess, Treasure Valley, so that Ada County AOI and the Napa County AOI.
Okay, and that helps me to understand. It seems like that it would be downstream of the Williams pipeline, so it's closer to your load, so it doesn't impact the capacity of Williams to transport natural gas during peak loads.
right. The Rexburg and the Nampa are actually behind what we refer to as behind the gate, so they're actually on our distribution system, so
Right.
they don't require upstream capacity.
And then Plymouth, it sits on, I'm just going to speculate, I should look. It sits on the Williams line, so when
Yep.
they provide capacity into Williams, they vaporize the gas and put it into the Williams system.
Yep, it sits right on a hub that is in Plymouth, Washington, which is along the Columbia River. And so they can deliver gas in about 5 different directions, or one, 2, 3, I guess 4 different directions. So it sits right on that hub, and that's where they liquefy and inject into their system. And then we use our TF2 to deliver it to our system.
Okay.
That's the Stanfield hub?
No, it's not Stanfield. Stanfield is Northwest Pipe and GTN. It's north of Stanfield, on the other side of the Columbia River. It's right along the Columbia River, right as you cross over on Interstate 86, I believe.
84, right? So
84. I can't remember what 86 or 4. I drive there enough, but I can't
or you
remember.
go
the
down the
freeway names.
I-82. It's kind of, where that interchange is.
Yeah, it's right on the river there. So
Highway 11, Washington side.
And then with respect to your contracts, you indicate that it's a T2 contract. And so that gives you higher priority then? Is that how that works?
It's called a TF2, and it just gives us priority to deliver that storage. Yes.
To your load. Okay.
To our load. Yes.
Thank you.
Yep. Okay, next. So we've talked quite a bit about it, but obviously liquefied natural gas, we liquefied at -260, and it takes up a lot less volume. So it's stored in large tanks. And I'll show you a picture of one of those tanks here shortly. But it's almost pure methane. So through the through the liquefaction process. It has a high withdrawal rate capability, and so that's why we can use it for those needle peaking days, because we can get it out quickly. The pipeline can get it out quickly, so that's why our contracts on those TF2s also are for higher amounts, and so that's why it is ideal for those really peak days in order to meet balancing and integrity issues. The opposite, liquefaction is slow. It's an intensive process, and there's high cycling costs as well. It takes more effort to liquefy natural gas than it does to just store in underground type facilities. There's no methane released in the atmosphere process. It's all contained and reused in the boil off process, and they recompress it and inject it back in. And this is the Plymouth facility that I was talking about. There's actually 2 tanks there, so I assume that this picture was taken from the top of the one tank to the other. And like I said, it's right on the river there in Southeast Washington. And that tank pretty much looks identical to our Nampa tank, but our Nampa tank's smaller. And so underground storage, a little bit different again. It's injected under pressure in these developed salt domes. Takes a little more development to build those fields. The maximum daily withdrawal is less than liquid storage, but it still provides a good cycling kind of injection where we can inject and withdraw quickly and at a lower cost. So we talked about the locations. Obviously, Nampa is behind our gate on Intermountain's distribution system. Plymouth is on Northwest Pipes system. Rexburg is on our system in eastern Idaho. Jackson Prairie is in Washington on Northwest Pipe system. And then Clay Basin is on Questar, which is now Mountain West. So those facilities are kind of across the region. And I think I have a map to show you where those are. And so you can see Rexburg in eastern Idaho, Nampa right here in the valley, Plymouth in southeast Washington, and Jackson Prairie over in the western Washington area. And this is just a quick look at the amounts that we have in there. So quite a bit of storage that we have over the winter, and it equates about 28% of our load. So we can kind of count on that amount. So we just don't have to buy as much for the winter load. That's kind of reduced by our storage capacity, and just shows the maximum withdrawals that we have there. As you can see, that Plymouth, like I was talking about, the capacity there is 155, 175 a day. And so that's why we can meet those really big needle days, is because of that capacity on that Plymouth. Then this is a look at the other chart that we looked at a little bit earlier, but it just kind of adds in layers of a little more additional detail, showing the needle peaking stuff maybe that we could use from Plymouth, the storage and winter gas that we use is layered in over there on top of what we would do for winter base load. And then of course the injections in the summer in order to meet that winter demand. So it's kind of a mix of all the resources that we have together. And did we miss one marker? Or no, I'm behind, I think. I think you're good. So questions, Kevin? Looked like you had another question.
Yeah, I'm kind of curious about the nature of the fill, what we would call the fill season. So in the past, when market price was predictable, for lack of a better word, and there was not a lot of natural gas consumed for power burn, typically once we got through the cold or heating season, then gas was cheap and you would use that, buy gas to do fill. But over the last few years, what we've seen is that with that increased power burn and other demands, that appears to me to not necessarily be the case anymore. So it doesn't really work as a hedge. Is that fair to say, or how do you see it?
Yeah, so I see your point there, because last summer we saw a lot of that, right? Last summer pricing was pretty high. And part of that is what led to this winter crisis, because as a utility, though, we really have to have it operationally. So there's kind of no choice in that. But there were a lot of marketers that delayed putting storage injections because the price was pretty high last summer. However, I will say that as a utility, we're still looking at pricing, and we still would consider it a hedge, but we're trying to utilize it more during the lowest time. So like May and June, for example, are great times to inject for us as a utility. And Intermountain's injecting a ton into Plymouth right now because the pricing for May and June was lower, and it's based upon our WACOG too. Yeah. And so May and June are better times, just given that hydro is really rolling right now. And so, and pricing kind of ticks up, kind of that July timeframe where more power consumption is done by the power gens. So we try to focus more, getting more in there in those months where pricing is low, and then focus less on the months where it kind of ticks up in late summer.
Thank you.
Sure. Rick.
Yeah. So could you maybe go into help, or could you kind of explain your hedging of contracts for forward prices and such, and how far out do you go, and how do you capture, like now, lower prices? And then I guess there's a coordination with the means to take and get transport to your system as well, a combination of both. Could you maybe explain a little bit of that?
Sure. So that the hedging portfolio is handled primarily by our AMA, our asset manager, which is IGI Resources. And what they do, is they're always looking at the market and the market analysis that they have. They have a model that they have, and so we have some base load supply arrangements that we've done, but then IGI can act when pricing is lower on those hedges. And so it is a 3-year portfolio. And so they're always looking at it all the time in terms of interacting with that 3-year plan. We provide them with a forecast for the year. And then so IGI is acting on those hedging opportunities during the year. And then we also provide them with an update at the front of the month, so they can plan storage or additional supply accordingly. So it's a yearly, a monthly, and then a daily too. We also provide them with a daily forecast, so they can plan on storage or purchasing gas on the day.
The reason I'm asking is, given late 2022 and early 2023, the significant price increases associated with natural gas, just trying to understand, your approach to that. Are you kind of exposed like everybody else to those high prices, or is there enough hedging in place that helps to temper those prices, or a combination of both?
Yeah, it's definitely a combination of both. And I would say Intermountain was in pretty good shape because Intermountain was somewhat isolated from that pricing at ACO, because ACO wasn't nearly affected. It was the Rockies and Sumas that were affected. So it depends upon the utility. We also have Cascade. Cascade was more affected, even though we do hedge a portion of our portfolio. I think Intermountain's in that 60 to 70% hedged from the last figure that I can recall. And so I think they are pretty heavily hedged going into winter. And so it does keep that exposure down. But Intermountain has a good position in terms of where their supply comes from, unless, ACO spikes, of course. So every utility has a little bit different balance in terms of where their exposure is, depending upon where their market pricing is. So Intermountain was actually positioned pretty good this last winter.
Okay. But you do source from the Rockies then as well, though, correct?
Yes, yeah.
And
they were exposed to some day pricing in the Rockies, even though, they were trying to utilize storage as much as possible too. So.
Okay, thank you.
Yep. Anyone else? Okay, turn it back to you, Mark.
Thanks, Eric.
Yep.
Thank you to all of our presenters and for the great questions that we received today. Remind everyone again that please feel free to submit comments anytime at irp.comments@entgas.com. The sooner you can provide them, the more likely we're able to act on those. Our next meeting will be August 2nd from 9 a.m. to noon. We'll be covering potential capacity enhancements, resource optimization, our planning results, and discuss the remaining IRP process. If there are no further questions or comments, I thank you all for your participation today, and we look forward to seeing you in August. Thank you.
Thank you.
Thank you.